A very good morning to all. Myself Dr.A.Mydeen Bibi, Assistant Professor, PG and Research Department of Mathematics, the Standard 5X Rajaratnam College for Women. I am here to give the explanations about analytic functions and complex analysis. Today we are going to learn lot of the things about analytic functions. First I want to give the learning objectives in analytic functions. In this session we are going to see about definition of analytic function, Cauchy-Riemann equations, properties of analytic functions, determination of harmonic conjugate, Milne-Thomson method. First I want to give the definition about analytic functions. We need to call about analytic functions as a holomorphic function or regular function. First I want to give the definition about analytic function. A single valued function f of z, we are defining a function f of z, is said to be analytic at a point z0 if it has a derivative at z0 and at every point of some neighborhood at z0. It has derivative in every point of its neighborhood. Also, if it has analytic at every point of the region, then it is analytic in the region R. Here I want to give the necessary condition for complex function f of z to be analytic. Derivation of Cauchy-Riemann equation is an important role doing in derivation of necessary condition for a complex function f of z to be analytic. For the derivation of Cauchy-Riemann equation, the statement that is I am taking one complex function f of z, that is f of z is equal to u of x comma y plus iv of x comma y is analytic in region R of the z plane, then we need to prove that the two conditions, that the derivatives exist and also at every point of that region the derivative should be satisfy the CR equations, that is Cauchy-Riemann equations. I want to prove the necessary condition for a complex function f of z to be analytic, that is the derivation of Cauchy-Riemann equations. The proof, that is I am taking one complex number f of z, that is u of x comma y plus ib of x comma y. First I want to assume the analytic function it is analytic in the region R. Then by the definition f of z, it has the derivative f dash of z. So we need to find the derivative of f of z. So I am finding the derivative of f of z, that is f dash of x is equal to limit delta z tends to 0, f of x plus delta x plus minus f of x divided by delta x. Here I am giving the derivation of Cauchy-Riemann equations. We know that f of z is equal to u of x comma y plus the imaginary function iv of x comma y. I am giving the derivation first f dash of z. In that session I am going to give two cases. First case is delta z tends to 0, that delta y equal to 0 and delta x tends to 0. And the second case I am taking delta z tends to 0, we now assume that delta x equal to 0, I am taking delta y tends to 0. In both the cases I am deriving two equations. From the two equations, from 1 and 2 we get ux plus ivx is equal to minus ivy plus vy. From this equating, I am equating the real part and imaginary part, we get ux is equal to vy and uy is equal to minus vx. These are called the Cauchy-Riemann equations, that is CR equations. Therefore, the function f of z to be analytic at a point z, the first condition is its derivative must exist and it is necessary that the four partial derivatives should exist and satisfies the CR equation. Next, I want to give the sufficient condition. We already known the necessary condition for f of z to be analytic. I am now giving the sufficient condition for f of z to be analytic. Statement. I am giving the first statement, that is sufficient condition. I am taking one single valued continuous function f of z, that is u plus iv is analytic. If it is analytic, I am giving the sufficient condition for this. For the sufficient condition, it must satisfy the three conditions. First one is its partial derivatives are exist. The second one is the partial derivatives are continuous, and the third one is this satisfies the CR equations, that is ux is equal to vy and uy is equal to minus vx, real and imaginary part at every point of R. We already known that all the polynomials, trigonometric functions, exponential functions are continuous. So Cauchy-Riemann equations, we know the Cauchy-Riemann equations. So in the Cauchy-Riemann equations, if you are having the theta constant, so it is in the polar form. So I am going to derive the Cauchy-Riemann equations in polar form. The first one is I am taking f of z as u of r comma theta plus iv of r comma theta. In the previous function I am taking f of z as u of x comma y plus iv of x comma y. In the polar form I am taking f of z is equal to u of r comma theta and iv of r comma theta. In the polar form, we are taking the derivatives as r and theta. I am deriving the conditions for Vy and equating real and imaginary parts. I am deriving Ux and Vy. In the place of Ux and Vy, I am having Ur and V theta. So I am deriving Cauchy-Riemann equations in polar form. So I am giving one example for your reference. If I am taking the analytic function f of z is equal to z cube, first I am defining in the simple function, next I will prove the polar form. First I am taking the simple function f of z is equal to z cube. I am going to prove that it is analytic. We all know that for to be necessary condition and sufficient condition for the function to be analytic is, first one is partial derivatives exist, and the second one is the derivatives are continuous, and the third one is satisfying the CR equations, that is Cauchy-Riemann equations. First I am taking the real and imaginary parts and I am finding the derivatives, that is unless that CR equations are satisfied, I am checking. So here I am taking Ux, Uy, Vx, Vy, all are exist and all the derivatives are continuous. I am also satisfied that the CR equations are satisfied. Hence the given function, simple function f of z is analytic. A simple example must prove the conditions easily. Next I am taking the example for polar form. So r and theta, in the place of x and y I am taking r and theta. I am taking f of z as log z. For f of z is log z, I am taking the polar form z as r e power I theta. So log r plus log e power I theta. I am deriving f of z. I am taking the real and imaginary part, u as in log r and v as in theta. I am deriving the continuous, partial derivatives are continuous and satisfying the CR equations. It's a simple example, but it should be very useful to you to learn polar form as satisfying the CR equations. Next, I am giving the simple explanations about Laplace equation. We are going to use is an harmonic functions. The first I am defining two form of Laplace equations. First one is Cartesian form and the second one is polar form. First one is del squared phi is equal to 0 and the second one is polar form in the r and theta terms where I am defining the Laplace equations. The next two important thing is harmonic functions. In analytic function, harmonic function plays a important vital role. A real valued function of two variables x and y is said to be harmonic if the second order partial derivatives, we already defined for the analytic, only we are taken the first order derivatives, that is ux, uy, vx, vy, and it is continuous and it is satisfying the CR equations. For the harmonic functions, we are going to derive the second order partial derivatives. The second order partial derivatives exist and they are continuous, and the Laplace equation in the place of CR equations, I am going to satisfy the Laplace equation for harmonic function. Yes, conjugate harmonic function. It's a very important thing. If u plus iv is an analytic function of z, then v is called a conjugate harmonic function of u, or u is called a conjugate harmonic function for v, and u and v both are called conjugate harmonic function. Next I am giving the important properties of analytic functions. I am giving lot of the properties here, orthogonal curves, like that. The first properties may be play a role in real and imaginary functions of analytic function, that is harmonic functions. The converse of the above results need not to be true, and the second property must be an f of z is equal to u plus iv is an analytic function. Then the family of curves u of x comma y and v of x comma y where a and b are continuously constant. And the third one is property 3, the analytic function with constant modulus is constant. Next, I am constructing an analytic function. We all know what is analytic function. I am going to construct an analytic function using the method, Milne-Thomson method. It's a very important method. I am defining the conditions of Milne-Thomson method to find an analytic function f of z. First, I am defining two conditions. First condition is in real part and the second condition is for imaginary part. The next, when we using the Milne-Thomson method, we can use the method to find the harmonic conjugate too. I am defining a function f of z is equal to u plus iv be an analytic function. From this, I am integrating the part yn in terms of x. I am taking that. I am giving one simple example to prove the Milne-Thomson method. It will be useful for you all to derive the Milne-Thomson function, Milne-Thomson method to derive a function as harmonic function and analytic function. I am giving the polar functions too for the Milne-Thomson method. I hope you all enjoyed this session and you all get lot of the information about analytic function. It will be help you to find the harmonic functions using the Milne-Thomson method, and also I am deriving the property sum. Thank you so much.